Okay. Any question about the in the previous session, our objective was to finish the autoregressive models, but this section was not covered, so we started this session and then go to the variational autoencoders. Okay, we want to talk about one application which is very suitable for models that can have exact density estimation. You will see in the future that some models cannot provide you with exact density. Sometimes they just give you a lower bound on the density or likelihood level. But autoregressive has a nice property that they can give you the exact density. You can calculate it, and we talk about how to calculate the density. And we also talk about this slide that there are some adversarial perturbations that, in the sense of visual appearance of your image, they cannot be understood. For example, you cannot differentiate between these two images, while in the right image, this perturbation is added to the clean image. This is the clean image. This is what captured the camera. Then this noise is added, and this is the final result. And you cannot see even the perturbation here. But a model, even a state-of-the-art model, cannot differentiate between the content in these, provide different content for these two images. This one is stop sign, this one is the yield sign, and the only reason is this perturbation. Okay, so how can density estimation help you with this issue? How it can be used to detect such images, okay? These are some examples images for different methods. For example, this is a random perturbation, this is FGS, and these are all methods to design this adversarial perturbation. There are different approaches to design it, okay? These are those methods. What can I do with a deep autoregressive model? Assume that I have a deep autoregressive model trained all over CIFAR 10 dataset, okay? So each image you give me, for example, from the training set, assume these are the images from the training set. If you give me this image, I can give you the probability that the model assigned to that image. Okay, and then we have lots of these images inside the training set. Let's say instead of the density, we calculate the minus logarithm, negative log likelihood of that data, okay? Until the last one. In the last one, again, I calculate these numbers. This negative log likelihood has another nice interpretation. That interpretation is the number of bits needed to encode that random variable. As a simple case, assume I have a binary random variable. For example, it can be 0 or 1. Each of them with the probability 1 over 2. This is the states, okay? If you take the negative log likelihood of this value, negative log likelihood is the 1 over 2. This number is something called NATS. NATS may not be very meaningful for you, but if you divide it, because all of the logarithm we write here are in the natural basis. But if you divided this number to the logarithm of 2 in the natural basis, or in other words, if you calculate the minus logarithm in the basis 2 of the likelihood, you have something which is calculated in bits. It means that this is the number of bits needed to encode this random variable. And we know that a binary random variable can be encoded with how many bits? With 1 bits, because 0 or 1. 0, 1, 0, 1. 2 states. And this is exactly 1. Now scale it to an image, okay? This is just a justification for how we can interpret it as the bits, okay? This number is the number of bits, it is the nats, because it is not, it is in the logarithm of natural basis. If I divide it to logarithm of 2 in the natural basis, I have minus logarithm of this value in the 2 bases for all of them. And this number is in bits. It means that conceptually you need this amount of bits to encode image number 1. It can be related how to uncertainty affect the number of bits. It is not the target. I just want to say what is this bits per dimension here. Okay? And then if you divide it to the dimension also, the dimension of image, it means that you are calculating the number of bits needed to encode each dimension on the average. Okay? This is what exactly they write here, bits per dimension. It means that it's a measure of like negative log likelihood. It is exactly equal to negative log likelihood, but with a minor difference. What is that curve? The most important curve is this one. What does this curve show? Assume that I change each of the training samples into their bits per dimension, this value. So, for each of training sample, I have a corresponding bits per dimension value, and then I plot the histogram. For 60,000 images, I have 60,000 bits per dimension, and then I plot the histogram there. This is the histogram, and it is divided to the total number. Okay? So, start with the labels. The clean train. This color is the clean train. You cannot see it because it's behind the clean test. Okay? Here. The clean test. The clean train and test are really overlapping. What does it show? Yeah, exactly. We have no overfitting because exactly the bits per dimension for the training and test is similar. If the bits number, the bits, yes.
Can you go over that? I'm confused. I didn't get what the argument was here.
You understand the x-axis? What is bits per dimension? Okay. You know, if assume that I have a trained model and the model is overfitted, what does it mean?
It has low variance but high bias, right? Yeah.
No, in terms of compare the training and test. In terms of comparison between training and test, it means that the negative log likelihood for the training is very low,
Right.
but it is not low for the test.
Right. Okay.
You know, and then in that case, the gray curve here should be skewed to the left side. Why? Because it gives better negative log likelihood to the train, while it is not suitable for the test because it is overfitted.
Okay.
It makes sense? Okay. But the important another important point is that how the adversarial perturbation affect this curve. If they change the images, can your model understand that the distribution is shifted? The answer is yes. It means that if you shift, for example, with randomness, the green curve, your distribution comes to here, and it is completely differentiable with the training and test sets. It means that if you put a detector here based on the distance between these two curves, you can easily understand that the data with the high probability is coming from a random noise added to the clean images. And also other types of attacks that visually they cannot be differentiated with the original image, but it's see that you can see here that they can be easily differentiated. For example, this BIM method, it can be easily differentiated with the clean data. You see? But here you can also qualify the attack methods. For example, these two attacks are very efficient in the sense that they do not change the distribution very much. It can be easily used to detect, yes?
So the value that we get out of it is we can be able to detect the adversarial examples.
Yes, and also you can qualify the adversarial attacks. Each of them is capable of changing the image while the distribution is not changed very much. All of them are in the metric with a view to your model, you know? If you train another model, maybe more capable model, the place of this distribution change. For example, in this model, which is, I think, a pixel CNN, in this model, the ranking is in this order.
But isn't it more useful to be able to map an adversarial example to something that has not been affected by the adversarial attack? Yeah,
that's also let's say desirable approach. But for that approach, we will see that we have score generative models. That score generative models can easily recover the original distribution given a sample from adversarial attack. Yeah, we will see that some methods can easily do that, and you recover the original distribution. Yeah, but with this case, the best performance, the best use case is to evaluate how the distribution are changed. Yeah. Yes.
We are training this on the train data and test data, so we get a distribution from that.
Yes.
But if it is not an adversarial attack, and like if we get an out of order distribution example and train it, and if we get examples for those samples that are out of order for the train and test data that we have used, so doesn't that distribution be away from the training test data?
You mean that we extend the training data set with samples coming from these attacks?
No, I'm saying suppose how are you going to differentiate between adversarial attack and this out of order distribution?
If you also work on the out of distribution images, you will also see the similar effect.
Yeah.
You will see that the distribution is also differentiable with the original data set. Yeah. It means that this is just the use case of robustness, but in the case of OOD, you can also see the similar effect. But it is more important to design and to select a good P of theta that can show you these types of results. For example, if you've used, for example, a simple nade or made, it can't generally lead to these types of results. Yeah. The model is more important. It is very important. Yeah. Any question? Yes.
Can you please go over why negative log px means the number of bits required?
Yeah, for an image, it is really hard to show that. I show it with very simple binary sample. If I have a binary sample, I know that the number of bits needed to encode this random variable is 1 because it has 2 states. Okay. If I calculate the negative log likelihood for each of them, negative log likelihood is 1/2, but we know that logarithm are in the natural basis in this course. If I divide it with the logarithm of 2 in the natural basis, it means that I'm calculating the minus log likelihood in the 2 basis. This value is the bits needed to encode this random variable. This may not be achievable for a limited sequence. It is an information theoretic challenge, how you can achieve this number. But for our simple case, it is easily achievable too, because it's equal 1, and we know that by 1 bits, I can differentiate between 2 states of this random variable, 0 or 1. This shows the number of bits. Here, what happened? Here, show the number of bits to encode each pixel of the image. In the general sense, you use 8 bits for the R, 8 bits for the G, 8 bits for the RG and B. Now it says that it is not needed that much of bits. In the efficient case, you may need just 4 bits to encode the pixel instead of 3 times 8 bits, you know. But how it is achievable, it is a trick, and it is not trivial. Yes?
How do you encode the dimension? I didn't get that. The bits and the bits per dimension. What is the dimension again?
The dimension of image.
Oh, the dimension.
Yeah. Then the bits needed to encode each pixel of the image, it means, yeah. Any question? This is also how effective are these methods. It shows that for the clean image, you have this, this is the error rate, okay? You have a acceptable error rate. When you add a random noise, your error increase a little, but for the methods that are designed that are intended to design the attack, you will see 100% error rate. It means that all of your test set, for example, BIM can deteriorate your inference on all of your training sets, test set, excuse me. And it is very interesting because the change that they apply is really understandable by the human, and human can bypass this perturbation, but the models cannot and become totally garbage models. Any question? Okay, and the summary of autoregressive. The idea is to use chain rule to factorize the joint, and then we parameterize the factors instead of having a table over the factors. We parameterize using a neural network, and then we use the KL divergence as the distance metric, and you see that it leads to the maximum likelihood estimation. And we also use Monte Carlo estimation to approximate the distance. We know that the distance should be expectation with respect to the model, to the true data distribution. Because we do not have true data distribution, we sample from the true data distribution. It means that we select the training sample, and then using the Monte Carlo estimation, we estimate the distance. What are the pros? The most important point is easily probability estimation. You will see that even for the variational autoencoders, you cannot easily estimate the exact density value. And easy to train and monitor. It is very important point because you can easily calculate the negative log likelihood over the validation set and stop whenever the negative log likelihood is increasing over the validation set. And it is easily monitorable for training. And the cons is the ordering requirement. If you have an image, it is not trivial how to select the ordering. If you have sequential data, it's more suitable. And also the sequential generation. You will see that, for example, in all of them, you should generate one by one. It means that the problem with ChatGPT that you can see that you cannot see your response all at once. It is generated sequentially. It is this problem of all autoregressive models because the generated first element is used to calculate the probability over the second one. So you cannot, without generating the first one, generate the second one. Okay? And the high-level representation is not here. It's a problem. We talk about the tasks were density estimation, generation, and latent variable or high-level representation. That we do not talk about high-level representation here. And in the next session, in the next presentation that we start now, you will see that we have high-level representation. Any question about the autoregressive models? Okay, with this slides, we finish our topics to be covered about autoregressive models, and you see them that they are easily understandable than, to some extent, they are more easily understandable than other methods because they are solely built on chain rule, and chain rule is a very well-known topic in statistics. In the next session, in the next presentation and next model, we want to talk about variational autoencoders. They are really nice models, and they are based on our intuition how to model data in a simpler way. These are the topics, not important. We will go through all of them. Again, consider the iris flower dataset. We have three types of iris flowers: setosa, versicolor, and virginica, and each of them has two physical features, petal and sepal. And this petal and sepal has a width and let's say length. Yeah, the width and the length. This is the plot of this data set, the plot of the petal length versus the petal width. If you load this data set in your Python, you can easily find all of these features. Now assume that you are in a labeled, currently assume that we are in a label regime. In the label regime, we have these, let's say, data points. This is each of the flowers, and you can see that they form some clusters to some extent. But now we have a label data set, so we can easily see those clusters. But now assume that the data is without label, and you are given, this is exactly the same. I just omit the labels. Looking to this data set, assume that now I want to fit a model, to train a generative model for this data set. Okay. The simplest case is to assume that I want to fit a Gaussian distribution for this data set, and the result is, as you can see, this is the position of the maximum position of the density, and this curve shows how it spread in the space. It means that in this black curve, the value of PDF is 0.2. You know, although in this point, this is logical, but because of the limitation with your models also give high probability to these points. You see? And it is not desirable. So, what can we do? One thing that we can do is to assume that, again, to consider the label data set. If I have the label, if it is a condition, we see that we do not have the label. If I have the condition, but in that case, I can easily fit a Gaussian distribution to each of the labels, you see? And it is very well fitted to this data. Visually, we can see that it is very well fitted, but with, for example, considering a training and tested, we can also confirm this intuition. And this is the case for all of the data. You see, all of them can be easily fitted if we have access to the conditional data distribution. Condition on the label, if we have access to the conditional data, we can easily fit a Gaussian to all of them. But the problem is that if you fit a Gaussian to the complete data set, it is not a good option. Yes?
Can we put into like a higher dimension and
go to the higher dimension and
would it be easier to cluster then? I don't know.
Look, the objective is not clustering. You know, at the end of the day, you should give me a probability to each point in the data space, in the original data space, which show the probability. You know, this is my objective. Okay. So condition on the label, I can easily fit the Gaussian to them, but the Gaussian cannot be fitted to all of them. And my objective is to do this this fitting. What does it say? It says that assume that you have just access to the unlabeled data. Can you do the same? Can you, to some extent, understand the label, and then fit a Gaussian to each of them, and then put them together to have this distribution? This distribution is really desirable because it gives low probability to this point, where we do not have data, and high probability to data to the point that we have dense data samples. It is desirable. And our objective is to understand whether we can do a procedure like this with 3 Gaussians here or not. Okay, the intuition, what is the intuition? The intuition is to combine simple distributions to create a complex one. This is, you can see easily the intuition here. I have a Gaussian distribution, which is very simple for me, and then I built another distribution. These are not 3 separate distributions. This is one distribution, you know, and I just put these curves to show that where each of them is located. But at the end of the day, you have just one distribution. So I have a very complex distribution in terms of Gaussian in comparison to Gaussian, because Gaussian has just one maximum, one local maximum, but it has 3 local maximum, while it is built on Gaussian. It means that it uses simple distributions to build a complex distribution. This is our intuition, and we want to see how we can create complex distribution using simpler ones. So you may be familiar with GMM, but if you are not familiar, we will go through it in this presentation. Do not worry. So assume that I want to create this complex distribution. Assume that I have access to 2 types of distribution, one categorical and one Gaussian. Then we generate each samples as follows. First, I sample a Z from categorical distribution kata with parameter pi. Then the samples are generated using this conditional distribution. This is not very complex notation, you know. This says that if look at the Z selected. If the Z selected is 1, it means that you are generating samples using the normal distribution over the data with this mean and this covariance matrix. This is the way I create my complex distribution. And how is it a complex distribution? If you calculate the marginal, you know, the conditional is very easy. The conditional over the data, given the we call it hidden or latent variable. We will talk about why it is justified this name. The distribution given the latent variable is very simple. But this is not the data distribution. This is the conditional data distribution. What is the data distribution? The data distribution is this value where you marginalize out the latent variable. It means that you calculate the summation over all possible z for a given x, and then you calculate the probability of x. And you can see here that the complex distribution is built here. You will see that we have a combination of Gaussian distributions. And this is exactly what we have here, a combination of Gaussian distributions, a combination of 3 Gaussian distributions. Everything is clear till now? Okay. So we have this complex distribution. While the Gaussian distribution is unimodal, this distribution is multimodal. It has 3 peaks. So it is desired because maybe our data are concentrated in 3 different spaces, in 3 different parts of the space. The situation becomes more challenging if you have something like this. In the case of Iris dataset, we have just 3 let's say groups of data. Here we have 25 groups of data, and here if I fit a Gaussian here, it is not working because you see that it gives high probability to here, but for example, it is high probability here, which is not desirable here, and you easily see that this is not a good option for this dataset. But if I can use the similar approach like GMM, then we can have this distribution, and it is nothing except a GMM with 25 components. The previous one was 3 components. Here is 25 components. Everything seems simple, but the most important point is that you do not have access to Z. Z is very, very challenging here. What is Z? How can I select Z? How can I understand? Even someone give me, for example, we know that samples here may be associated with a specific value of Z. Maybe because it's one of the components, and our intuition that each of the component is corresponding to a value of Z. How can I understand that value of Z if someone give me a sample from this point? These are the questions that we will answer during this presentation. So what does we now talk about just GMM? GMM is very flexible, and you can build on a simple distribution, you can build complex distribution, and it is based on ancestral sampling. It means that you first sample from a simple distribution categorical and then sample from a conditional distribution. The condition is not clear here, but this Z show that this is a conditional. It means that you have access to the Z variable. And assume that for the case of iris dataset, each Z can be associated with the type of the flower. You see? In the simplest case here, if I can fit these three components, each of these components, and can associate each of the components with a value Z, assume that all of these observation comes to have a Z value equal to 1. And then the second one have the Z value equal to, and the second have a Z value equal to 3. It is very abstract information because I know that the samples coming from Z or or which are in this component are samples of, for example, I don't know which of them, for example, Setosa. And instead of all the information, I can just talk about the Z, because the most important point about each flower is its type, because we know that all of them are iris flowers, and this component is Setosa, for example. So this is the latent representation. It means that the latent information is very important for us. And for example, if someone can give us this probability, it means that given a data distribution, it is not the same as the above. The above is the probability of data given Z. Here is the probability of Z given data. It means that I give you a petal and sepal length of a flower, and you talk about the Z. For the flower, what does it mean? I give you one data point in this space. I give you one data point in this space, for example here, okay? And then if you can talk about this distribution, what is this distribution? How can I model it? This is a distribution over a categorical distribution with 3 categories. So you can model it with two numbers, and the third one is so that the summation is equal to 1. So you can give me that, for example, the probability for if Z equals 1 is Z equals 2, and if Z equals 3, you give me all of them. For example, this is 0.1, this is 0.2, and this is 0.7. And then I can easily understand that the most probable Z corresponding to this point is the Z corresponding to the training data samples corresponding to, for example, Setosa, or each of them that the data is here. We know that there is no label here, but conceptually assume that I want to compare how these Z can be used. So this is also a very critical information. Something, it may not be very clear now, but during the presentation you will understand how they work. Here I have a very simple example. It means that I have just 3 types of flowers that I do not have access to, and then condition on each of them I have one Gaussian distribution. Now assume that I have the images here instead of X, which is a 2-dimensional random variable. I have images of face. I have assumed that I have a data set of faces, 1 million faces. Okay? For the iris dataset, for the petal and sepal length, I do not remember what was the features. For that case, we see that a categorical is enough. Now assume that I want to extend and this concept into the case where X's are face images. For example, 68 by 68 images of faces. What do you think of Z in that case? We do not know anything about how we calculate Z, but what do you think of Z, a suitable Z could be in that case? In the case of flowers, Z encodes to some extent the type of the flower. You know? But how here we can extend the concept of Z? The data set of faces in general may be very complex. If you give me a data set, number of images of faces, I can fit a distribution to that very challenging. But assume that I tell you that this is the face of a man from this pose, with this age, with this, for example, background, with this, he has, for example, eyeglasses, he is to some extent, and every high-level information of that man. You can better imagine the image X, you know, in comparison to the general case, where I do not talk about anything. I just say that these are faces. But assume that condition on some information about the type of the face, the age, the sex, let's say the length, the height, everything about the man. What happened to your understanding of the image? You can narrow down the number of images you imagine. Is it correct or not? This is the concept we are following, and we want to encode when we go from GMM to variational autoencoders. Everything is clear? Okay. So this is our intent. Assume that in the Z variable, we have some concept. We do not design this concept. This concept will be designed during the training procedure. But assume in the background that there is a Z, there is a random variable Z that you do not access to, but that Z is encoding high-level concept of the image. And then condition on those information, you can better and easier model the distribution, because the distribution is a condition on the high-level information of the image. They tell you that this is a man, this is the tall man, this is, for example, from this type of pose, for example, his age is Falan, his age is something else, okay? So you can easily narrow down your distribution. Does it make sense? Okay. This is our objective, but everything is complex now because we do not have how we can encode the pose. In application, we do not design them, but our intent to train a variational autoencoder to encode them in the Z variable. Okay, and one important change is that the Z here is a simple categorical. But can the Z here be also a simple categorical? No, because the number of abstract information for the face images is much more richer than for example, a simple 3 types flowers, you know? There are lots of high-level information about a face. And this prior distribution, we call it prior distribution, this prior distribution must be capable of representing them all together. So the extension is that we transfer from a simple categorical here to a new Gaussian distribution here. Gaussian is this is continuous, this is the dimension here is just 1, but this dimension is a vector, z here is a vector, you can see it. This is the I just took for the simplification of the notation, I write it in this way. This is in Rm, it means that it is m dimensional, so it is much richer than a simple categorical distribution. And a condition on that z, condition on that high level information, I assume that the distribution over what you observe is very simple. It is a Gaussian distribution. The mean and the covariance matrix are a result of the latent variable or z. It means that z is entered into a function which has the parameter theta, and then it generates both the mean and the covariance matrix of a Gaussian distribution, and then you sample from that distribution, and that sample is the phase. Okay? Yes?
So z is a vector or something?
Yeah, exactly. Z is a random vector of dimension m. Yes, with a Gaussian distribution, but it can be any distribution. Yes?
Does each number channel corresponding to one category, or so you say it's m, right? Does this imply this m categories, or
when we are talking about variational autoencoder, we do not generally design this information. We assume that in its nature it is doing in this way. But this is just a background, a backbone for the variational autoencoder, and it is not clear how we can design Z such that the first element is corresponding to pose. But the most important point is none of them are categorical anymore. They are continuous random variables. They are coming from a Gaussian distribution. It is continuous. Because we want to have much more flexibility than GML. Okay? Any question about the concept and how we can, how is it supported by the idea of latent variable? Okay, then if I give you an X and an image, and then you can talk about the Z corresponding to that X, it is much more abstract level of information. We do not know. We can at the end of this presentation we will see that how we can design concept in the Z space. But currently, just as a for example, I think I do not have. Assume that I train a variational autoencoder over mnist digits. Then if you plot the Z corresponding to each of the mnist digits, we will see that how we can understand Z for each X. Then you will see that in the Z space, you have almost 10 categories of data, and they are much more separable than the original data, and they are corresponding to the type of the image you will see in the mnist dataset. This is 4, but for mnist you have 10 groups here.
So also, how do we select n? So if n is too small, then it's so.
It's a hyperparameter, and it's dependent on the dataset you are training. Yeah. As n increases, your flexibility is increased. Yeah, because this is the most important, one of the most important factors in the flexibility of the model. Yeah. Yes.
When I train the model, do I have to choose I take these specific attributes in an M or
No.
We do not choose the attributes. The attributes are just conceptual understanding of variational autoencoder. Then, after we train them, you will see that, for example, how we can understand the concept of, for example, wearing glass. We will see that how you can understand the vector of wearing glass. And if you add that wearing glass to any image where the person has no glasses, and then you add it in the Z space, you will see that the image changes such that the person is the same, but just a glass is added to his eyes. Yeah. Yes.
Can you say like each of these features, close, gender, age, are categorical themselves, or you could like another way?
They are in their nature categorical, but to allow the model to vary more flexibly, we assume all of them to be continuous. It means that in their modeling we assume every concept is continuous. Yeah. Any question? So, and the model specification. We have a latent variable distribution p theta of z. You will see here that the p theta, the z is also parameterized. It means that the latent has some parameters which are the model parameters. We know that theta is the total parameters of the model, and the parameters for the latent are these two parameters, mu z and sigma 2 z. So we have m variables here and one variable here. We have total m plus one variable here, which are as in our theta set, in our theta vector. This is the latent, and conditional observed distribution is a Gaussian again. And you see that if I have the concept, I can model the distribution over what I see in the reality with a simple Gaussian distribution, because I have the concept. I narrow down my options. I am not all the faces, just a very special kind of faces. And it can be done with a Gaussian distribution. Maybe all the faces cannot be handled with a simple Gaussian, but if you narrow down your latent for some types of images, then you can easily say that the result is a Gaussian distribution. Make sense? Okay, and where the neural network come into role, here you design these the mean and the covariance matrix using neural networks. It means that you have the concept. Concept is fixed. There is a neural network that designed the mean for the conditional observed variable. This is NN alpha. It means neural net alpha with the parameter alpha. And also there is another, let's say, neural network which has the parameter beta. And if you input z to that network, it's go through the network, then generate a vector, and this vector is go through a sigmoid. This sigmoid is to let's say to guarantee that the resulting vector is positive, and then the diag of that positive vector is the covariance matrix. We need the covariance matrix is diagonal, and we need the covariance matrix each element to be positive on the main diagonal because it's a variance. Okay. And the parameter of the complete model is mu z here, sigma 2 z here, alpha here, and beta here. So we do not know, and z is not the variable of the model. You do not want to optimize with respect to z. Z is a random variable, and we have no optimization over z. Does it make sense? It is completely different from this parameter. Z is a random variable which is not observed. It's a hidden variable. Okay? So do not consider it as a parameter of the model. Yes?
Two questions. So if getting your covariance matrix, you're using the DAG function, then is that really a covariance matrix? Because like everything else is just going to zero, just interested in that.
You know, this control the flexibility of the model, because you assume that it is diagonal. But for the diagonal matrix, it is valid because it assumes that each element on the main. You can also, instead of sigmoid, you can use ReLU. It also outputs, for example, positive values, and it is zero or positive values, and it is favorable, and it is enough. But in the case that you want to assume that a general case. You want to design the triangular, upper triangle of the covariance matrix, and we know that the covariance matrix is symmetric, so the lower triangular is not needed. The most important point is that you should design a valid covariance matrix. Covariance matrix has some properties. For example, it is positive definite. And imposing that at the output of a neural network may be challenging. You want to design, for example, the upper triangular part of the matrix such that the resulting complete covariance matrix is positive definite. But in this case, it is easy. We know that a diagonal matrix here, the element on the main diagonal is positive, they are positive definite.
How is a Gaussian distribution defined with a covariance matrix, not just a single value variance?
It's a covariance. It's a random vector. It's a Gaussian vector, and there is a relation. Maybe I do not remember correctly, but there is a constant here, and then the covariance matrix is used here.
Explain it.
Yeah, I do not remember that. The covariance matrix is here. Sorry for the place. And this is transpose, the result is a number, and then it's go through the exponent and the factor here and generate the PDF in the point X. Yeah. This is a random Gaussian vector, and it needs a covariance matrix instead of a variance to be defined. You mean the difference between covariance matrix and variance? The variance is just when you have a one-dimensional, but here we have a n-dimensional random vector. Yeah. Okay, and let's talk about the generation first. Density estimation is very challenging here, and this is the topic of training we will talk about. But the generation is very simple. How? You sample from the prior over the latent. There is a sampling module. We know that how we can sample, for example, but the sampling is not the topic of our course, but it is very easily sampling from a Gaussian distribution. Then the sample in the latent, you give it to the neural net that generate the mean. Also, you give it to the neural net that generate the covariance matrix. You will see that the output go through a sigmoid, then a diag, then you have a matrix. Again, you have a sampler. The sampler accepts the mean and the covariance, and this is the distribution over the observed images or observed inputs with this given latent. And we know that with this latent distribution over what we observe is simple Gaussian, so we sample from it, and this is a valid sample from that distribution. Now we assume that there is a trained model. For example, there is a model trained over a nest, and then if I go through this procedure, I have another MNIST image here. How the things becomes, let's say, tractable by selecting a latent variable. Latent variable is the most important point here. And you will see that the idea behind, for example, some diffusion models is also, again, similar to variational autoencoder, some types of them. Okay, the high-level representation, remember that this is just talking about the Z, and we know that Z is a high-level representation of the data. This is the conceptual information about the data. If we are talking about the face, in Z we have is the man, is the woman, is a man, is gender, pose, and anything information high level. But what are the challenging point here? Now I can say that, so when I have Z, when I have an X, I know that Z is a very interesting information. So I can reverse this process to understand Z? Is it possible, assume that I sample X from here, someone give me a sample X from this procedure, can I understand Z given X? Just with looking at this procedure. You have an X, that X is coming from a normal distribution. Now you should estimate the mean and the covariance matrix of that distribution. I have X. The first question is here. We are looking in a deterministic viewpoint. We want to know, can we reverse this procedure or not? At the end of the day, this is not the way we understand Z. Okay? Assume I have X. Are these arrows possible? No. They are possible with very high variance. Very high variance. Assume that you have one sample from a Gaussian distribution and they ask you what is the mean of that Gaussian. You can't tell them that the mean is exactly that X, because the mean is the position of highest probability. But it has a high variance. So the second term is very hard, but assume that we can consider that the mean of that distribution is exactly the X you observe. But the challenge is that most of the neural networks are not invertible. If I have mu theta of Z, I cannot tell anything about the Z. Most of them, we know that. Because they have some bottlenecks, information bottlenecks that narrow down the size. So you cannot make, having the output, you cannot say anything about the input. You will see that some models are trained such that they are invertible, but here they are not invertible. So understanding the Z with just having access to X is not possible in a deterministic look to this procedure. So let's talk about how we can understand the Z during this presentation. You will see that we will design some models that can tell us about the Z and its density. So although they are very flexible and they are conceptual, but understanding the Z, which is the most important point in those models, is not trivial. Okay? This is the challenges with Z. So the generation was very simple, but how is the density estimation? The density estimation is the place that you see there that there is no free lunch here. Assume that we have access to both p theta of Z and p theta of X given Z. So I can easily have the joint, the distribution over the joint. But this is not the density. The density is the distribution over just what I observe. It means that X. To calculate what the density over what I observe, I should integrate out, I should marginalize out the latent. It means that I give you an image. What is the probability of an image in this model? This is the probability that assigned to this image, the summation of the probability assigned to this image, condition on each of those Z. It means that I should get the joint of this X and Z for all of the Z, possible Z's, and then sum over all of them. This is the probability of this X. Okay? But the most important point is that the integral is not tractable. This is the integral. This is Gaussian, very easy, but assume that we have the multiplication of two Gaussians and the relation is in this way. It is very challenging and is not. There are some, you may be familiar with LGS, linear Gaussian systems. In linear Gaussian systems, these two relation are affine transformation, and the integral can be calculated tractably. But here, because we use very complex neural networks, the result of this integral is not trivial, and this is the problem. We have very flexible model, but you cannot estimate the density very easily. And this is where we have some problems. Yes?
I don't get why this integral is intractable.
Look at the integral. It is very strange integral. The integral over z of a normal, we know that what is the formulation for a normal. Again, a normal you should calculate this integral. This integral is tractable when, for example, if you assume a simple, in the simplest case, if you assume here that the covariance matrix is not dependent on z, excuse me, and the mean is just a linear, is a affine transformation over z, this integral is tractable. But here, this is the neural net with parameter alpha. And it is very hard. It is intractable. But if it was simple, the resulting of this model that I talked about above is the linear Gaussian systems. They are very well studied approaches for these flexible models. But here we are talking about a model that the mean and the covariance matrices are hard, very hard defined in terms of neural net. This is the diag here, very complex.
And x here is a vector, yeah?
Yeah. It's, if you have images, you vectorize them. Yeah. You know, the joint is not important for us. The joint is not important because I want to know how probable is the data I observe under this model. So I need to calculate the unconditional distribution x. And this is the challenge, yes?
And assume that we can calculate this integral.
Yes.
Okay? So if x is a vector, we have to use the chain rule to calculate the whole p theta of the vector x.
Yes.
No, I would just want to make sure that... Like,
This is chain rule.
No, chain rule on the elements of x.
You want the density over each element of x?
Yeah.
Okay.
So because like this integral, this normal distribution is x, we know the new theta and this kind of stuff. So this normal distribution will give us the vector.
Yes.
Okay, and it's multiplied in p theta of z.
Yes.
So the integral of a vector, like...
this gives you an integral. The result of this multiplication is function of two vectors. One of them is d-dimensional, which is x. One of them is m-dimensional, which is z. And you integrate out z. It means that m dimension is integrated out.
So the result would
is d. So this is exactly what we need for the x, because x is d-dimensional. Yeah. You know, one important point about these models is that they do not assume any ordering. They are modeling the data distribution with looking at the complete input. It is the power of this model. It is not rely on, for example, chain rule, because if you want to use chain rule, for example, in autoregressive, you need the ordering, and then the ordering imply some points over your data. There are some challenges for images, but here you do not have those challenges. During this variational autoencoder, we start by talking about challenges, and then we solve those challenges. We have about, I think, 8 challenges, and we solve each of them one by one, and the final result would be variational autoencoders. So the first challenge, what is the first challenge? The first challenge is that unconditional distribution is intractable. How can I calculate? Because if I want to fit, why I need this distribution, this density estimation? Why do I need this density estimation? Assume that I want just to use generation.
Don't need to calculate Z, then you want to sample X.
No, Z, you sample from the prior, you have Z, and then you enter to those networks, and you have distribution over X, and then sample X. It's not needed. And for generation, you do not need density estimation. I said why I need the density of the data, observed data. This is one of our tasks, density estimation. Assume that we do not want that task. Just we want to generate with these models. We need the density estimation for learning. Remember the autoregressive models? The learning of autoregressive models was maximum likelihood estimation. And the only things that you need for learning was to density estimate in the point. And here again, for learning, I need to know how probable are my data under this model and then change the parameters such that the probability is maximized. So the density I need for learning, okay? Make sense? Okay, the first challenge, the density estimation, the negative log likelihood, the density is intractable. So how we can solve the density estimation? The first one approach to solve it is to cast the likelihood as expectation. What does it mean? This is why I need the density. I need to minimize the negative log likelihood, so I need the density. But I know that the density is intractable, and things, if you can calculate it for one time, maybe it becomes tractable. But during the training, you want to calculate this integral as a function of the parameters for several times. So it is not a feasible solution. You should think about some alternative. So let's cast it as an expectation. How? The data density, we know that the data density is this integral, and if I condition this joint over the latent, and times the latent, I mean that the Bayes rule, I have this integral. Look at this integral. What is this integral? This integral says that we know that each integral that has the PDF for a random variable of a function of that random variable, it means that you are expecting that function with respect to the variable. Here is again the similar. Remember the expectation of a function f of z. Our notation was in this way. Z coming from p theta of z. If I write down this expectation is exactly this one. Is it correct? So look at this integral and the integral I write here. The first is exactly the same. It means that you are estimating, you are expecting this function, the conditional, with different z. I can write it in this form. It is the expectation of the conditional of what you observe over the latent coming from the data distribution, the latent distribution. What does it mean? Assume that I want to calculate the density of the face that you give me. What I do, I start to sample from the z, possible z's, calculate the conditional of this x. The condition of this x is very easily calculated. How? What was the conditional of x given z? It was a Gaussian. If you have the high level information, z, the distribution is simple, it's a Gaussian. Let's first talk about how can I estimate an expectation? Monte Carlo estimation. Monte Carlo estimation says that the expectation of a function with respect to samples coming from this distribution is, instead of the integral, you can samples from z, and for those samples, average your function. This is exactly Monte Carlo estimation, okay? So in this case, I can estimate the data distribution. Does it make sense how I do? You give me an x. This x is a face image. You give me a face image x. Okay? To calculate the probability of the probability that model gives to x, I should do the procedure here. I start sampling from the latent. Is it possible? It is very simple because it is a Gaussian. It is a Gaussian. I can sample from it. Assume that I have k samples from this distribution. Then Monte Carlo estimation says that this logarithm, no. This p theta of x equals 1 over k, the summation over I of, is it easily calculated? Can you calculate this number easily? Yes, because I have z, I know that this distribution is normal over x with the parameter p theta of zi, and covariance matrix, I call it sigma theta zi. You start sampling, give them to two neural networks. They generate the mean and covariance of this distribution, and then you calculate the PDF of your x point, your image you give me, in that distribution. It is a number, and I average over all of them. If k go to the infinity, I am exactly calculating the data distribution in the point x. If not, I am estimating it. Yes.
So that means once you set your prior period of z, that's it. It will never change.
Yeah, the prior distribution is not, the time is not changed, but it has parameter. It means that during the training, it may be updated. You are designing. In several cases, they assume that the density over the latent is fixed. They assume that it is normal, standard normal with zero mean and identity covariance matrix. But here we assume that it has parameters because in the general case of variational autoencoders, it has parameters. It says that the probability of your data is the average probability condition on different latent use independently sampled from the latent. Assume the faces, you give me a face. I want to calculate the probability of this face. I start sampling from the latent, and conditional on each of them, I have a density, a value. So for each of your samples, I have a value. I average over all of them. It is your density, unconditional density. It to some extent makes sense. But in the next session, we talk about importance sampling, which is another approach. But think about this approach. I start sampling from the latent in an independent way, and on the other hand, I calculate the probability of the image you give me, conditional each of those samples from the latent. It means that, for example, I sample from the latent, it is a man, for example, his pose is something, for example, A, B, and C, for example, he's smiling or anything else, and then I calculate the probability of your X given this Z. If they are aligned, it gives you a high probability. If they are not aligned, it gives you a low probability. In the average, you are calculating what you need. which is the unconditional density of the data. Thank you very much.